Hello everyone. Today we're going to talk about how to optimize the Kalman filter properly and how not to accidentally cheat when we compare it to a neural network. So the Kalman filter is used to estimate the state of some dynamic system from a sequence of measurements. So at a certain point of time, we think that the state is somewhere around X, and then after some time, we think that X changes according to some modeling F of the system, and also the uncertainty grows a bit. But then we get a new measurement, Z, and we can filter together the new information from Z with the previous distribution of X, and then we get a new estimation, xt plus 1. We do that repeatedly, and this is the Kalman filter, which maybe you know as the set of mathematical equations here at the bottom. Now, to use the Kalman filter, we must set the parameters Q and R that represent the noise of the system. If we don't have the data that's a whole problem, well studied, and that's a whole another story. But if we do have the data, we can simply calculate the noise as the covariance of the noise in the data. Now, like pretty much everyone else, we wanted to improve the Kalman filter using a neural network. So we focused on the linear modeling F, and we replaced it with a recurrent neural network. And then we optimized the parameters of the neural network using the data. And since we already have an optimization procedure, we also optimized the parameters Q and R of the Kalman filter itself. And we got better results. And we were happy. And now then we noticed that we did two different things. We added a neural network and we optimized the parameters of the Kalman filter. So we decided to do an ablation test. We removed the neural network and we only optimized the parameters Q and R. And we actually got better results. Not just than the Kalman filter, but even better than the neural Kalman filter. And this was quite shocking for us because we optimized the parameters of the Kalman filter and got better results. And then we added a neural network, and this actually made things worse. And this has several important implications. First, we took the very standard Kalman filter since 1960 with the very standard tuning method given the data. And we improved its predictions just by optimizing the parameters using standard supervised learning. And this is pretty useful. Now, second, this is not supposed to be actually possible because the Kalman filter parameters Q and R as the estimators of the noise, they are supposed to be already optimal for the prediction errors. The thing is that this is only true under the Kalman filter assumptions, and we discuss in the paper and show that these assumptions are practically, they never hold. And in fact, sometimes it's pretty tricky to even notice the violations of the assumptions. And when this happens, there might be a very large deviation in the optimal parameters of the Kalman filter. Finally, just like we did, many other works also implemented their neural networks and showed that they are better than the standard non-optimized Kalman filter. And just like in our case, you cannot actually tell whether the neural network is truly better or is just more optimized than the Kalman filter. The only way to tell is to optimize the Kalman filter in a similar way to the neural network. So the main takeaway is that the Kalman filter assumptions practically don't hold. So you cannot really set the Kalman filter parameters just by estimating the noise of the system, because that's not really a proxy to the objective of errors minimization. Instead, you must optimize the parameters directly for this objective. Now, as long as you optimize the right objective, I won't be picky about how exactly you do this, but we do have a PyPy package for that, which also takes care for you of the positive definiteness of the noise parameters, and you're more than welcome to use it. So thank you very much for watching.